So let's start today's session. Today's session is going to be on structural analysis, and we will basically finish our quota by looking at two questions, one related to indeterminacy, kinematic indeterminacy basically, and the second one is a very basic question on arches. Okay, let's start. So question number one, GATE 2017 set 2, question number 14. Consider the frame shown in figure. If the axial and shear deformation in different members of the frame are assumed to be negligible, the reduction in degree of kinematic indeterminacy would be. So basically, kinematic determinacy tries to tell us how many different number of ways in which a joint can move, right? Collectively in a structure, how many different number of ways a joint can move. And this question says that if we assume that there is going to be no axial movement and these members are going to be rigid, right? They are going to be inextensible. Then by how much will the degree of kinematic indeterminacy is going to decrease? So if you remember, so this is a 2D frame, 2D frame, and the formula for kinematic indeterminacy for a 2D frame was given as 3J minus R minus M plus RR. So the notations might be different compared to other places if you are looking at. So the J is actually number of joints, including the free end, right? Including the free end, including the released joints, everything will be included. R is the number of unknown reactions, support reactions. Right? Unknown. RR is going to be the number of released reactions. For 2D, if we have some, let's say, n number of released reactions, then it is going to be, now this is for hinge. So if we have a hinge at a point, so this is also called as releasing the momentum at this joint. So the RR for this case is going to be summation of all the number of hinges and M dash minus 1, whereas M dash is the number of members that are joined to make this hinge. So if 3 members are joining at a hinge in this particular structure, then we will have 2 release reactions. And you will be familiar with the other type of release reactions such as the horizontal release reaction, right? Then where the axial force is released. Then we have the vertical release reaction where one vertical reaction is released. So some of these you can revise, you can go back and revise. So this is the formula, but we have not talked about what is M. M is number of inextensible members. So this formula, if nothing is given to you in the question, then the kinematic indeterminacy is going to be 3J minus R minus, plus RR, right? But if they mention in the question that, these your axial and shear deformation in different members is assumed to be negligible, or they mention directly that the members are considered inextensible, in that case, M is going to be that number of members in which there is no axial deformation, and or which are considered inextensible. What we have been told that in this particular example, what will be the difference in your decay, the degree of kinematic indeterminacy, if we consider all of the members as inextensible. So simply we have to subtract the number of members from the existing kinematic indeterminacy. So we don't even have to find out the initial or the final kinematic indeterminacy. If you can just look at the number of members and count them. So we have 1, 2, 3, 4, 5, 6. So the new kinematic determinacy is going to be the old one minus m, which is 6. So the correct answer would be B. Okay. Now let's go to the next question. This is a classic question. Everyone, I think, should know the answer to this question. The figure shows a two-hinged parabolic arch of span L, subjected to UDL, uniformly distributed load, Q per unit length. Can be W, can be anything. No, it can be written as W also. Usually I have seen W. Now what they are asking is, what is the maximum moment in the arch equal to? So generally in our beam, if we were given this condition, what we will do, we'll try to find out VA, then this, then take particular section at a distance X, and then try to find out the bending moment as a function of X, then perform the derivative of this bending moment with X and put it to 0 to get the value of X. That is how you generally do it. But this is a special case. What is special in this? Special is the arch is a parabola arch and the UDL is spanning throughout the length. So when these two conditions are given to you and no additional load is given, what are the conditions? It can be either, the arch can be either two hinged or it can be either three hinged. Then the UDL should be for full length. Third, arch should be parabolic. If these three conditions are met, then we can easily say that the bending moment at each and every section in this arch is going to be 0. All right. So this is something that you should actually remember itself, because these type of questions, as you can see, GATE 2017 set 1 question number 7, they have been asked recently. So they can be asked in any type of questions, or one of the options in the multiple select questions, because they can ask what is HA. You should know WL square by 8H, right? They can ask what is VA, WL by 2. Then one option they can give what is BM. They can give any option, but 0, 1 will be correct one. So MSQ type of questions can be made from these kind of things. So you should be aware of this concept. All right, let's go to next question. So now that we have finished our daily quota of questions, we are going to look at some very interesting questions that I found from test series that shall be named anonymous. Okay, so let's look at this question. Consider the plane frame with an overhang as shown. Assuming negligible axial deformation, which of the following is correct? Assuming negligible axial deformation. What does that mean? That all the members are inextensible. So the M in case of the kinematic indeterminacy is going to be 1, 2, 3, 4, 5, 6. Okay, so what are the options here? Structure is externally stable. So what are the conditions for structure to be externally stable? We should have minimum for a 2D frame. So plane frame means 2D. we should have minimum 3, and they should not be uh, parallel and concurrent, right? The reactions. So what do we have? 3 at least. We have here, let's count the reactions. We have here vertical, horizontal, and momentum, and vertical. So in total, we have 2 plus 3 plus 1, we have 6 reactions, and they don't seem to be concurrent. So externally, it is going to be stable. How about internal stability? So internal stability, we can identify if we see any of the members rotating relatively with respect to any other, or we can check our static indeterminacy internal, that is 3C minus RR. So as you can see, there is no released reaction, and there is no kind of no loop. This is 0, DSI is 0. So we can say that it is stable internally. So these two options will go wrong. Internally unstable is wrong. So these two options will not be selected. What about this? The total degree of static indeterminacy, both internal and external, is so DS, which is DSE plus DSI, is equal to how much? So we have already seen that DSI is 3C minus RR is 0. What about DSE, which is R minus RE? So RE basically number of equilibrium equations. We will have 3, right? And how much is R? R is the number of unknown independent reactions. That is 6. So 6 minus 3, we have 3. Either you can use this, or you can use the formula which for the total degree of indeterminacy, that is 3m plus r minus 3j minus rr. So if you look at it, how many members are there? M, 1, 2, 3, 4, 5, 6. So we have 6 members. 3 into 6 plus unknown reaction 6 minus 3 into how many joints we have? 1, 2, 3, 4, 5, 6, 7 joints we have. The free end is also a joint. So 7 and minus release reactions is 0. So we have 18 plus 6 minus 21. That is 24 minus 21 barabar 3. So from this also we are getting the total static indeterminacy ds is equal to 3. You can do using either of these. Okay, so this is correct. The total degree of static indeterminacy, both internal and external, of the structure is 3. Very good. Now the ratio of total degree of static indeterminacy with the kinematic indeterminacy is 9 by 27. So we need to identify here kinematic indeterminacy. So for a plane truss, that is a 2D truss, what is the formula? So you should be able to remember that formula. It is 3j plus rr minus m minus r, right? 3 into, considering all the joints, 7 plus RR, this number of release reactions 0, minus M. What is M? Remember, number of inextensible members. So we have to consider, since it is not specified which member is inextensible, but it is said that we have to ignore the axial deformation. We are going to assume all the members are axially, or sorry, inextensible. So then m is 6 and minus r is also 6. 21 minus 12, what is that? 9. So if you take the ratio ds by dk, you have 3 by 9, which is also 9 by 27. So this option is also correct. All right, I hope you understand this. What you can do if you are watching the recording is you can pause, go back, and then look at this, because it is a nice question for a revision of formulas. Okay. Now let's come to more interesting questions. So I like the following three questions that we are going to look at, because when I looked at these questions at first, I myself was thinking this is a very big question. Why, this kind of question has been included? But the amount of trick and the amount of concept they have used to put in this question, I was, flabbergasted. I liked this question very much, and I want to share this question with you guys also. Okay, so this question is, the force in the vertical member of the truss shown in the figure will be. What is the only vertical member in this particular truss? This is the only vertical member, and they are asking us the force in this particular member only. So this is a truss. That means this is also pin joint. This is pin joint. This pin joint. This is pin joint. This pin joint. Okay. Anyhow, it doesn't matter actually if you are contradicted whether this is a pin joint or not. It doesn't matter for this particular question. Okay. Now I am going to tell you two concepts by drawing. If in a truss you have three members that are meeting, out of which two members are coplanar, meaning this angle is 180 degree. Okay, two members are coplanar, and there is any other member in between this place, in this space. So this is 1, this is 2, this is 3. Anywhere in between 1 and 2 and 3, if this member is there, and these two members are coplanar, and there is no external loading applied, then the force in this particular member is going to be 0. It makes sense, right? Because if you look at this point, you will do fx is equal to 0. That will give you something, and you will do fy is equal to 0. That will be some component of this force 1 into some angle cos theta or sin theta, let's say sin theta, will be equal to 0. So f1 is going to be 0, right? From sigma fy is equal to 0, we can easily see that the vertical component of a force in this particular member has nothing else to balance it out, because there is no external load also. So the force in this highlighted member is going to be 0. Second point, if two members are meeting at this point, again no external load. Let me write also, no external load. Okay, two joints are meeting, and the angle between them is between 0 to 180, means they are not coplanar. Okay, means they are not coplanar, and only two joints are meeting, two members are meeting at a joint, and there is no loading, no external loading. Then the force in both these members is going to be 0, right? Because see, consider this as horizontal and this as some angle. So if you look at this second joint, second force in the second member, there is nothing to balance the vertical component of this force. If there is nothing to balance this vertical component of this force, which we get from sigma fy is equal to 0, then this from the expression which we get from sigma fx is equal to 0 will also give us f1 is equal to 0. Right? Simple. So now that you know these two concepts, which I had also forgotten, and when I first looked at this question, I actually started solving it, and it gave me a lot of problem. But if you know these two concepts, sorry, you know these two concepts, then just by looking at this question, you can see that this is a point. Two coplanar members are meeting. Whatever, even if it is 90 degree, even if it is having a load at this point, it doesn't matter. At this point also, it has to satisfy fx is equal to 0, fy is equal to 0, right? So this member is not going to be having any force. So f of vertical is 0. So see, very clearly you can see that each of the points in the truss has to satisfy these two equations. You may be conflicted by looking at a force here, but remember it has to satisfy the equilibrium equations at this point also. And if you look at just this point, you can clearly see that there is nothing that is going to give support to the vertical force applied by this point. So that means there won't be any force that will be developed at this point. Correct? In real life, there will be, because see, this kind of some kind of deflection will be there. So this component and all those things will make up a force. But in our gate syllabus, there won't be any force. So F vertical is 0. 0 is the answer for this question. All right. Now look at this question. This question also looks, very intimidating. But after applying the concept, you will feel like, oh my God, this is a very simplest question. Okay. Now let's look at this. The deformation of the truss member is shown in the figure. So each of these members, CB got contracted by 2 mm, BD got extended by 4 mm, CD got contracted by 4 mm, AB got extended by 4 mm. They are asking if these are all the cases, and AD they are not saying anything. Basically, if AD is going to have anything, any contraction or movement, then this support will move. So that's not happening. So they have not given. So we are going to say AD is having 0 mm contraction or expansion. Okay. Now when this is given, what they are asking is what is the horizontal and vertical displacement of this joint D particularly. Now do you remember one important concept, that if you are given the contraction and elongation of all the members in the truss, then if you want to find out what is going to be your movement, final movement of any joint, let's say in this case B only, in horizontal direction, then what you have to do, you have to apply a unit load in the horizontal direction or whatever direction you require, and you have to calculate the particular force developed due to this unit load in all these members, and simply the deflection, horizontal deflection in B is going to be summation of all the forces generated by this unit load in these members. So if you denote K as a force, so KAB here, KAD here, KDB here, and then multiplied by the corresponding displacement that you have. This simply is your displacement in horizontal direction in your joint P. Similarly, for vertical in B, you apply a vertical unit load. So Ki into delta I again. So delta I is going to be same only this K value is going to change because of the direction of the load. Okay. Now what is asked? We have been asked what is the vertical and horizontal displacement. So let me again make it 100%. Yeah. Now what I want you guys to pause the video right now and see, are there any redundant members? Are there any members? So for before we do that, let me, since we know already that all the deltas and this delta is 0, let me draw For horizontal, we are going to put 1 Newton or 1 kilonewton. Let me put just one unit force in this direction at B. And for vertical, we are going to put a unit force in this direction. Look at these two loading conditions and tell me, pause the video and tell me if you can identify that do we need to calculate the K, that is the force developed in each of the members. Do we need all these members actually? Just look at it. All right, so I hope you pause the video and you try to look at this. Now, using our concept that if two joints are meeting at a particular point where there is no external load and they are not coplanar, then the forces in these two joints are going to be zero. So do we have any of this condition here? We definitely have. As soon as you realize that, this question becomes piece of cake, right? Okay, so there will be some vertical. So I'm going to just name them V1, H1, V2, H2. Similarly here also. Okay. Now here V1 plus V2 is equal to 0. Here H1 plus H2 plus 1 is equal to 0 from summation Fx is equal to 0. Right. Now let's take a moment also at our point. Let's say which point should we take? Let's say at point B only. At this point itself, we take the moment is equal to 0. So we have, or maybe we can take, yeah, it will be easier if we take the moment at this point is equal to 0, because almost all the forces, most of the forces are going through this particular axis, so we don't have to worry about them. See, V2 is going through this, right? V2 is going through this, V1 is going through this, H1 is going through this one force that we applied, that also is going through. What does that mean? That means that H2 into this 4 meter is equal to 0. That means H2 is equal to 0. And that means H1 is equal to minus 1. So this H1 we have here as minus 1. Very good. So now uh, let's look at these two members. So we have we have D here, B here, and A here. So looking at this joint A, what can we say? H1. And let me draw the forces also. So let's say the forces are like this, right? Tensile forces. So, sorry, here. H1 plus F AB is equal to 0, because both are in same direction, right? Depending on what the direction we have assumed. That means FAB is equal to minus 1, because FAB is equal to plus 1, because H1 is actually minus 1. Okay. Now let's look at joint B. See, we don't need to worry about this particular joint, that is the FAD, because this is between the supports and we know that there has not been any kind of elongation and contraction at this point. So we don't need to worry about that. So because even if you calculated FAD, the delta for that FAD is 0. And as we know from our formula, it is the summation of Ki into the delta I. So no need to find out that, no need to do extra work. Okay. At joint B, if you look at and put F y is equal to 0, what do we see? f of bd, f of bd into some, let's say, so this is 4 meters and this is 4 meters, that means this is 45 degrees. fbd sine of 45 degree is equal to 0. There is, because there is nothing to balance that. So fbd is also 0. Okay, very good. So even this member also is gone. This member has some k force, but we do not care because delta is 0. So let's write delta b horizontal. What is it? FAB into delta AB plus FAD into delta AD. FAB is 1. Delta AB is how much? Plus 4 mm into plus 4 mm. FAB is some K. Delta AB 0 plus 4 mm. Easily we can solve this question. Right? Very right. Now let's look at this particular case, trying to find out the vertical displacement. Again, we'll write the whole system fx equilibrium equation. So v1 plus v2 is equal to 1 in this case because force is going vertically downwards. h1 plus h2 is equal to 0. All right. Considering now the moment at this particular joint, same joint A, we can see that h2 into 4 plus 1 into 4 is equal to 0. V2 is passing through is no, so it won't create any momentum. H1 and V1 also passing through this point, so they also won't create any momentum. That means H2 is equal to minus 1, right? That means H1 is equal to plus 1, correct? Now let's again go to this particular joint. We do not care about vertical forces at this point actually, because vertical force, if we calculate, we'll be able to get this particular joint, this particular member force, and we are not very much interested in that member force, right? So we can go away with this itself. So h1 is plus 1 and h2 is minus 1. All right, and this is our 1. So let's assume tensile force again in all the members. F BD, F AB, F AD. All right. So this again at joint A, sigma fx is equal to 0. That means 1 plus f of AB is equal to 0. That means f of AB is minus 1. All right. Now coming to our joint B, what is unknown here? Unknown is our FBD. So if we put Fy, sigma of Fy is equal to 0, we can easily get FBD cos 45 degree is equal to 1, right? So FBD is equal to root 2. Okay. So if we know these two, let me move this a little bit left side. And then continue this horizontal line. Okay. Now we know all the forces and their corresponding deltas. So let us calculate the vertical, which is what? FAD into delta AD, FAB into delta plus FAB into delta AB plus FBD into delta BD. All right. FAD sum K into delta AD 0 plus FAB minus 1 into delta AB. Delta AB was plus 4. Yeah, so it is plus 4, then plus FBD root under 2 into delta BD. Delta BD is also plus 4. So it is plus 4. So we have our delta B vertical is root 2 minus 1 into 4. That is 1.658 mm. Now, since we gave the direction of our force applied to get the values of K as downwards, so this is actually a downward deflection. And in this case, we gave the direction of the force applied on the right side, right? On the right side here. So this is actually right side. So what is the horizontal movement of joint B? It is 4 mm to the right. What is the vertical movement of joint B? It is 1.658 mm to the down direction. So I hope you can understand that these kind of questions they only look scary, but if you just start to apply concept and solve them, they become very simple. All right. Now we'll come to our last question for the day. This is also very simple question for 2 marks. They can ask this question. You can get intimidated by this question very easily. Same as me. But then if you start solving this question, you will realize that it is nothing. Okay, so let's look at this question. For the truss shown below, member PR is shorter by root 2 mm. So it was short, but they somehow extended it and got the fixed the member in this particular location. But the delta is actually plus root under 2 mm. It got extended by root 2 mm. Okay. The magnitude of vertical displacement of joint R is. Now they are asking what is the vertical displacement at joint R. Similar question as above question. But what they have told, all the other, indirectly they have told to us, all the other members are fine. Only this member was short. And because of that, what is the vertical displacement of joint R? What do we know from our experience? If we want to identify any displacement in a truss, we know that we have to put a unit force in the required direction and then identify the force in other members with respect to that force. Okay, one more major hint that they have given to us that you may not realize in exam because of tension is that all the other members are fine. So when you are applying a unit load, as you should, let's say I apply on this upward direction of 1 unit load, you don't have to find the stresses that is developed in all these members. Because why? Because delta of all these members is 0. Only delta for this member is known to us, that is root 2 mm. Okay, I think you understand this. Now let's try it. So what does that question now boil down to? The question now boils down to what is the force in this member? That's all. Let me highlight it again. The question now boils down to what is the force in this member because of a unit load that we have applied. Right? So now let's try to solve this. Okay, again, use that concept that I told earlier, using which we can remove the non-zero force members. When you use that concept, you will see that these two are meeting but without any external load. So zero force. Similarly here, one more is here. These three are meeting where these two are coplanar. That means this is also zero. So again, this question boils down to a very simple truss, which is just a triangle with two, um, with two supports, a simply supported truss, and then you have only three members here, right? So even if you don't know anything here till now here, you can clearly see that there is a symmetry in this particular question, that on the left hand side is same as the right hand side. So because HA is going to be 0. Why? Since Fx for this, from the summation of Fx is equal to 0 for this whole truss, you will see that there is nothing to balance this particular horizontal reaction. So HA will not have any other force to balance this, so balance it. So H is going to be 0. That means this particular truss will have two vertical reactions here and one here. So it is a symmetric force, no symmetric section. What can we use that for? We can say that both the forces are going to be F. And from the figure, from this particular figure, we have seen that this is 4, this is 4. That means this angle is 45 degree, right? So this one unit load that we applied, so if we want to do sigma Fy is equal to 0 at point R, we will have 1 is equal to 2F cos 45, right? So 1 is equal to 2 by root 2F. F is equal to 1 by root 2. Newton, kilonewton, whatever you want to write. Okay, 1 by root 2. So we have then identified the force in this member, the force developed in this member. So then what is the value of your delta? Delta R vertical, what is it? It is going to be sigma Ki into delta I. All the delta i's are 0. Only one delta I is there, that is plus root under 2. And only one Ki we needed to calculate, that we have calculated 1 by root under 2. So what is the magnitude? It is 1 mm. Alright. So the vertical movement of this particular joint R is going to be 1 mm. So I hope that I was able to, develop some confidence in you guys to solve these kind of questions, because I know the more number of members we see in a truss, the more our confidence get decreased, right? So if you can just look at this question, look at the questions with a calm mind and try to apply the concepts, then I think you'll be able to solve most of the questions. All right, so that's all for today's session. Thank you and have a nice weekend.